get going. Come in. Okay, well, today's Friday. We're going to talk about some topics that are relevant to chapters 3 and 4. Right? Testing equal variances. So we have a two-sample t-test. Implicitly, we made that assumption that it was equal variances. Okay? Or you could do a thing that is unequal variances. And you might do more of a formal assessment. So how do you do more of a formal assessment on the variances? Equal or not in two samples. So there's 3 ways of doing that. We'll kind of describe how those get done. There's a couple other things that if we have time I would like to look at. I mean, to kind of put in there, you know, what do these different impacts, these different deviations and things, what impact do they have on our tests, right? Or tests or confidence intervals. Right? And so you can simulate that with the computer. That's one aspect of using R. We can simulate distribution and simulate different variations. A lot of statistical papers that develop methods or try to analyze data with enhanced methods do simulations to show that their method is performing well. And there's a question of whether or not we should have a paired sample. So in some cases, right, you could take people and measure them before and after, or you could go out and just gather one group of people and then another group of people. So you can make a choice. Do you set your study up with pairing or not? What would be some considerations that we might deal with that? Right? So let's jump into it, the testing for equal variances. So when we had 2 independent samples, we could be interested in testing is the mean in one group equal to the mean in the other group. And our statistic that we're going to have, you know, y bar for the first group minus y bar for the second group, or the other way, but it's that difference, right? The variance of this difference in independent samples is the variance in the first group over N1 plus the variance of the second group over N2. And how we'd want to estimate that would depend on whether it's equal or not. Right? If the variances are actually equal in the 2 groups, we would probably want to combine the variability from the first group and the second group to get a better estimate of variance. Right? And then we can use a certain degrees of freedom. But if they're different, that's not going to be a good assumption. And this, putting a pooled estimate of these 2 things that are very different won't be as accurate. In particular, one of these would be much larger, and particularly if that large one ends up in the small group, then that variance could be bigger, so it won't be so accurate. But if we compare them and only have to estimate one parameter and use a larger degrees of freedom, that's generally good. So it's good to pool them and treat them as equal if that's reasonable. But if it's not reasonable, then you might want to look at the unequal variance or the Wilcoxon or some alternatives, right? So how do we go about testing that? So we want to test the null hypothesis that the sigma 1 equals sigma 2. And you can do this in terms of variances or standard deviations. It's the same hypothesis. Right. The group 1 has N1 observations, and we can calculate the sample variance for that group. Right. Group 2 has N2 observations, and we can calculate the sample variance for those 2. Right? Now, if the yi1 in that first group are normally distributed, and the yi2s in that group, 1, 2, are also normally distributed, right? Then the ratio of the variances probability distribution. George Snedeker, who was at Iowa State and North Carolina State and other places, did a lot of the developments for the statistic and testing variances. His motivations were in things in agriculture, field studies, and he was friends with Ronald Fisher, so he named it the F distribution, in honor of Sir Ronald Fisher, who did a lot of things back in the 1910s, 1920s with development of maximum likelihood and theories of estimation, and wrote a textbook for statistical methods for research workers. That was kind of a core book for training applied scientists. So this thing has a particular probability distribution. So I should say under the null hypothesis, under H0, right, that they're equal. Right, if these things really are equal, then this thing has an F distribution. And this F distribution kind of looks like this. It's a positive random variable. Right, everything in the numerator denominator has been squared, variances. And so it's all positive. And if you end up with a ratio here that's really small or particularly large, and it is skewed, so the areas are not symmetric. But if you end up out here in the tails, this is our rejection region. The rejection region. This is the area where we reject the null hypothesis. We reject the idea that sigma 1, the variances are equal. And so the p-value would be 2 times, if the S1 squared is larger, it's going to be 2 times this area. If we end up with a practical ratio that's less than 1, right, then it's going to be 2 times that area, and that'll be our p-value. So that's the standard variance test that gets done. So let's look at just a couple numerical examples. Right. But any questions about what we're doing or computing? So we're going to take the sample variances, and take the ratio. And under this assumption that the data were normal to begin with, we get a test, right? So for example, there's probably some way to set this to the narrow pin by default. I have to kind of explore that, right? So in a study of pediatric cholesterol, they have in 100 children, and these children, in this case, the father died of cardiovascular disease. And then n equals 74, similar aged controls. And in this group, ultimately you would want to test, is the cholesterol different in one group versus another? But if you're going to test that, you have to decide how you're going to do it, so you might also look at the variances. It turned out in this study that this is 35.6 squared. The standard deviation was 35.6 of measurement of cholesterol is milligrams per deciliters, right? And the S2 squared was 17.3 squared milligram per deciliter. Right? So the standard deviations, one's basically double the other one, right? And we have a fairly, decent sample size in each group. What would our test show us in this case? Just going through the mechanics of it. Right? So the F statistic, you take this 35.6 squared over the 17.3 squared ends up being 4.23. Right? So our null hypothesis, right, is that this is equal. Under that null hypothesis, this F distribution, it has 99 and 73 degrees of freedom, that particular curve. And this one, the cutoff point that has 2.5% up here in the tail for that one ends up being 1.55. And we're out here somewhere at 4.23. That's not really drawn to scale. Okay. That's the edge of the page, right? So 4.23. And that's not really going to scale. It's kind of way out there. The F distribution with larger degrees of freedom is really centered pretty tightly about 1, right? Which would be the equal variances under the null hypothesis. And in this case, they're quite different, right? So we'd have to conclude here to reject the null hypothesis. The variances are not equal. So in testing the means, we might use the 2-sample t-test with unequal variances. We might use that Wilcoxon rank sum test for comparing two groups that does not assume equal variances in the groups, right, instead of an equal variance one. So it gives us that result in these cases. So just a different numerical number. This is in a study of children with lead exposure. Right, there were two groups. Group 1. These children live less than 2 miles to a lead smelter. And group 2 were children in the same city that were more than 2 miles, maybe it's less than or equal to more than 2 miles away. And so the ultimate interest could be, is the blood lead measurements of the children who live closer to that pollution source, is that going to be higher? And also for those children, if they have more exposure, higher blood levels, do they show testing differences, at an early age? They do dexterity tests with kind of finger tapping tests and spatial reasoning tests, and just a whole host of different things can be done. Right? In this particular study, the standard deviation for the first group was 12.05. The standard deviation for the second group was 13.16. Right? And so standard deviations are often reported because they're in the same scale as the measurements, whatever blood lead concentration was. So our F ratio, if we take the bigger over the smaller, we would square those things, 12.05 squared. And so that comes out to be about 1.19. Right? We would compare this to the null hypothesis that the variances are equal. Under that assumption, this thing has an F distribution. Degrees of freedom are, now I put the bigger one on top, right? I put this one on top just to deal with a positive, something bigger than 1 and an upper tail. So the degrees of freedom, the relevant one is 34, because that one's in top, and there's 64, so 63 degrees of freedom. It impacts this shape and skewness. Usually 1's pretty much here in the middle, and the probability that we're greater than and 1.19 ends up being pretty much right about here. They're fairly large. Now I have it listed as a p-value of 0.54, so I think that this tail area, if it's a double, is about 27%. So maybe I've made it drawn it a little bit big. But getting a ratio of this size under this null hypothesis with these sample sizes is not terribly unusual, right? So in this case, it would seem perfectly fine to use a two-sample t-test with equal variances. Normality is also an issue for that one, so you might want to do a little more checking, but in terms of the variances, equal variances, if you're going to use that test, seems fine. Right, so you can come up with a decision. Often variability by itself will be interesting. So instead of just looking at the variability, more variability in this case would mean that some are very low and there's a few possibly that are very high. Right, those few high ones that get a lot of exposure could be as interesting really as just the average difference. Right? Any questions about it? But this test, right, comes about, right, under an assumption, right, that the data are normal. This strict probability relationship down here comes when you have normal samples, and then this variance is the normal samples with the squares of the deviations ends up being chi-square distributions, and ratios of chi-squares end up being f, and so it works out in probability theory, right? But if this is not true, then again this test might not be that useful, right? It could be influenced by high skewness or outliers, and so maybe it would produce a significant result just because of one or 2 points are sticking out really high that make one of these values really big, and it's not that making that good of a decision. In fact, the test of variances are pretty sensitive to like an outlier because things do get squared in all the variances, so a little bit more. So what can we do, right? So an alternative, if the data are non-normal in either group, you could look at an alternative. Right? An alternative test, less dependent on normality. And there's been a number of these developed in the literature. Our book mentioned something called Levine's test, Levine's median test. R implements something called the Brown-Forsyth test. So it's a modification of that one. And the way that this thing goes, right, if you have N1 in the first group, N1 and N2 in the second group, we're going to take the data and subtract the average in each group. And so that these are like errors or residuals. So we're going to take the differences to the averages in each group. Kind of center each group separately around its own average. And then we're going to calculate the medians of those. So we're going to take the median of all those observations that are in there, right? So not the average. The average deviation about the mean is 0, because all these deviations actually add up to 0, so the average is 0. The median, right? So if there's a bunch of small ones and a few big ones, the median will be below 0 with that clump that's small. Right? On the other hand, if there's a few very small deviations, right, and outliers the other way, then the median will be shifted away from 0. If it's all symmetric, it'll be pretty much right around 0. Right? So we take that, and then it takes differences, absolute differences, EI1 minus E1 tilde, so the difference to the medians, and we do that in the second group too. The medians are less sensitive to one observed outlier than the means. These are absolute deviations. Variances involve squares of things, right? And so instead of squares, there's absolute deviations, making everything positive on the same side. Right? We're going to take the average of those things. And then we're going to have a t-statistic, because these are averages now, they're kind of central limit theorem things. We're going to do a t-test where the average of the absolute deviations about the median of residuals here is the same as down here. And if these two things are pretty close together, it suggests there's kind of equal variance, equal spread. But if these things are very different, well, that's going to mean that some of these residuals have extremes one way or the other in comparison to the others. So it's kind of a thinking through a number of different things. And so some of these procedures, like, well, how did they come up with this? Right? It's kind of a whole series of things strung together. But you could go back and read an original paper or some more explanation. And if you study statistical theory and methods, you might dig into some of the implications of this a little bit more. So we're going to do that calculation. And we also do the standard deviation of these values and the standard deviation of these values, as we would for a t-test. On the next page, we'll do a t-statistic that's going to make advantage of these things. So for the null hypothesis that the variances are equal, the t-statistic, this Brown-Forsyth, so that little initial on it, we're going to take the difference between those two averages. Right? Should be very similar if they're both equal variances. A value S here, kind of a pooled version of a standard deviation. And we had N1 and N2 here. And this pooled one, the square of that is going to be N1 minus 1 times the S D1 squared plus, I'm going to run out of room, N2 minus 1 S D2 squared over the N1 plus N2 minus 2. And we're going to compare this to a t distribution with N1 plus N2 minus 2 degrees of freedom. So if we end up with a t statistic that's much different than, bigger than 2 or less than -2, approximately, if our statistic is if the absolute value of our statistic is large, then we're going to reject this null hypothesis that the variances are equal. So a bunch of transformations are done, right, to do that, to set this thing up. Using medians and so on is really aimed at not being sensitive to a big outlier. Right? So it doesn't require the data to be normal for this to work. Taking the absolute values puts everything on a positive scale, so it's kind of measuring spread, right, rather than just plus or minus deviations. If there's big variance, then you're going to get some of those values that are very big one way or the other. Right? And then, so it translates this question of testing about the variances into looking into this t through kind of a complex way. But let's look at a data example where we can see that. So in the second case study was teaching geometry, right? And it was either the conventional presentation or a modified presentation, and they looked at the time to do a certain type of problem, right? And generally the histogram of time look like? Do that again. Here's the histogram of time. But there's these two groups, conventional and modified. Right? And it looks like the conventional is taking less and the modified is shorter. But to do a t-test, we want to kind of assess, are these variances the same? At first impression, does it look like there's much difference in variance? The central 95%, I mean central 75%, right, from first quartile to third, that looks about the same distance. You know, neither one has that long of tails. They kind of look similar, right? They look the same numerically. I'm going to save the data for the conventional and modified into two objects here to make it easier. The standard deviation for conventional is 70. Standard deviation for modified is about 57. You could also look at just the, thinking about statistics. Right? Certainly the sample standard deviations are relevant. The difference in ranges, if there were big outliers, the range command gives the minimum and maximum, and diff just takes the difference in there. And so one's a little bit bigger than the other. Right? The conventional is a little bit bigger than that one. You could do histograms. One thing about histograms is that the histograms usually adjust the ranges to fit the data. So if you're going to compare two histograms, it's much easier if they're on the same scale. Right? So you can have the limit on the x range. So this is the range of all the data. So that's the con, and this is the mod. So it's kind of toggling between those two. It kind of looks like the same spread, but just reversed. This f-test that we've done, there's a variance.test in R. Help R.test. Compare two variances. Really kind of goes through that. To do it, if we do that, comparing conventional and that, we get this output. Right? In this case, we get an f value of 1.55, degrees of freedom 13 and 13, and it gives a p-value of 0.44. Not unusual. It actually gives a confidence interval for the ratio of variances based on that. And so this f-test would say it's reasonable. You can't really prove that the variances are different. So if you want to do a two-sample t-test, it would seem perfectly fine to use equal variances. And that's a little more powerful test. We'll talk about power in more detail, but it's generally more efficient to do that. The way that gets done, right, you could save the ratio of the variances. That's the F statistic. Here's the 2 degrees of freedom, 13 and 13, or 14 in each group. The F distribution with 13 and 13 degrees of freedom, you can get the quantiles. So, of my little curve, what are the different quantiles on a fairly dense thing? And you can do that plot of the densities. The dF is actually the density of an F distribution, and that's what it would look like under the null hypothesis. Where is our F statistic value? It's right there. So it's not that far from 1 under this curve. The PF is the probability up to this point. Since I'm above 1, I'm going to calculate 1 minus that. That's about that's about 2.22. And if I double that, it's about 0.44. And that was the p-value reported up here in that one. So it doesn't look like it's right. In terms of doing the Levine's test, right? Again, if the data are kind of non-normal, if they've been a little bit more skewness, there's some skewness in there, right? If you want to kind of confirm or check, certainly if this was focused on variability somehow, right? And that would be the point of doing this. This Levine's test, so how would I find this? Just going to Google, right? Levine's test for equality of variance is in R. A few sites that talk about it, right? And this one, oops, I froze it. No. There's some R documentation, right? So there's Levine's test. It happens to be in some package called law statistics. Right? So in testing the quality of variances, I guess there's, in the legal profession, maybe there were some issues about making decisions and how do you do that, so it describes what it is. If you install the package and then do help of the Levine.test, it gives you this output. But it gets used, the Levine.test, by putting your outcomes there and then some indication of the groups there. And then there's some alternatives to use median, mean, trimmed mean, and so on. Some variations on the test that people have explored. This help file, it tells you all that stuff in there. It deals a little history. Levine, 1960, proposed a test. That's a little bit more general. And then it gives some references, right? So here's where Brown and Forsythe suggested alternatives. And this is Journal of American Statistical Association, so you kind of grab that whole thing there and go search for that article. It's JSTOR. Right? JSTOR is a free online collection of old journals. I mean, old, 5 years and back. There's kind of a current window where you still have to pay for them, but then it's a repository. So this is the article where they described it and tested it. You can get a peep, in any case, that if you would go on through that, it would describe how they came up with this and some of their rationale and maybe some of their simulations to see how it works. So it's kind of amazingly quick how you can get some of these articles, particularly if it's a little bit from the past. And so Journal of American Statistical Association is still one of the top statistics journals for theory and methods and case studies and things like that. So, but yeah, there's a whole history there. So if you're in graduate school studying a particular topic, you might might read a bunch of these and see the original arguments and see if you wanted to make it a modification. Like maybe we should do this on a log scale, or maybe we should take do something else about outliers, like trim them so they're not so extreme. Getting that background and then thinking of new ways of doing it would be where you would come up with some ideas. But anyway, I'm not going to install that here just because of the things with the computers, but if you wanted to get it, you go under Packages and you want to install something, you just type the law stat in there, and then it will install a package. That is, put the set of commands on your computer, and once it's put on your computer, then you type library of law stat, and those commands are active in R. Right? And then you get the help, you can run it, and to run it you just put the time and the treatment groups that are there, and it tells you that it's doing a modified, robust, Brown, Forsythe, Levine type test based on the absolute deviations from the median, right? Which is kind of what we did, right? But that's the long name for it. It gives you minimal output. Right? It just gives you a test statistic, right? A t-value, 1.16, and then a p-value associated with that. Right? T-values of 1.16 are not so far from 0, so again, we don't reject. P-value was a little bit higher, 0.44 for the equality of variances test based on normality. This one's not quite as big, and that's what you get there. So it's pretty, with the variance test and the Levine test, you could quickly run these couple of things if you really wanted to compare. And in many cases, they'll give you similar results, either don't reject or reject. If the data are quite skew, with big outliers, maybe one will reject but one won't, right? Or maybe it'll be kind of close. P-values 0.05, 0.06, 0.04 really don't mean that much difference, right? But if you get some discrepancy there, the real message is look at the data think about what you're doing in testing and think about alternate presentations, because if you have small sample sizes, it could be sensitive to those things. You can do this, right? So if you wanted to take my description of this, right? Take these deviations, median, deviations, mean, standard deviation, right? And then t-statistic, and then this result. You could step through those things in R. If you do that, right, here's the deviations for that group. Oops. Deviations for the next group. Absolute difference from the median of those things. Right? Standard deviation, this is the equivalent formula for that. T-statistic, and the t-statistic value that I got is about 1.04. So maybe they're doing a little adjustment in there, a little modification somehow. I'm not totally sure exactly what. I have to dig into it a little more detail. But essentially we get the same p-value. I got 0.309, they got what was it? That's that one. This one they got not 0.29, and I got 0.3031. So I'm not totally sure what the difference between that one is, so maybe there's a little bit difference in how that modified Brown-Seich one is done in R versus my interpretation of how the command is done, but it's essentially the same message. One other possibility is to do a permutation test. For 2 samples. So these tests could be perfectly fine, but for every test, you don't necessarily have to use just one test statistic, right? You don't have to use the obvious one like ratio of variances. You could use ratios of standard deviation, you could do something else, right? Like the Brown-Forsyth and the Levine, they had a pretty complicated new statistic to test things. Right? So in this case, we're going to start out with the null hypothesis that the two groups have equal spread. And we're going to have some statistic that we want to look at that gives that. Now we could use this F ratio, the variance of the first one over the variance of the second one. We could, so that's like an F. Maybe we'll call, SDR, we'll call it the standard deviation ratio. These two, I have one-to-one transformation, which is the square of the other one, so it's not really that different. But you could choose something more interesting, right? So how do you evaluate that? So we compute these for our data. And then we want to ask, is the statistic value unusual for the null, for the H0, for the null hypothesis, right? If our statistic is really unusual for the null hypothesis, we reject the null hypothesis. Right? So how do we do that? Well, the permutation test says, well, if they have equal spread, we should be able to combine the data together, or at least some deviations. Right? So the permutation test, we're going to combine N1 and N2 data points together. if there's, well, so one version of this would be to say that there's no difference at all in these distributions. And from these, we're going to calculate a new value of the standard deviation. And then the other N2 values are used to calculate a second one, right? S2 star. Right? And then we can get new ratios based on that simulation. We can square those. Those are the star ones. And those are the star ones. And if we do this many times, we will get a sampling distribution. We will get a distribution under the assumption that they're equal. Right? Now, that's what I've programmed in here. And as I'm thinking about it, we might discuss doing it just a little bit differently. So implementing that, you could do it based on variance ratios or standard deviation ratios, maybe a different statistic we want. We're going to get that variance ratio 1,000 times under the permutations, or we're going to get the standard deviation ratio 1,000 times under the permutations. So we're going to set that up, and then do this loop. We're going to put the get the indices, and if we pick the first 14 we pick, the 14 we pick from this numbers will become the first group. And the ones that we don't pick will go into the second group. So this temporary of conventional, temporary of modified. Right? And we're going to take the variance ratios there, and then we're going to compare what we get in simulation, just random rearrangements, random permutations, to the actual. If our actual is extreme, we'll interpret that as meaning that we can't. It's not very likely we would get that under the null hypothesis. So we could run those things. I think I had these before, but start here, run that, set that up, run it, and the histogram looks like that. So our actual variance ratio here, about 1.55, does not look very unusual at all there, and the p-value is about 0.246. In this case, it doesn't matter if we use variance ratio or standard deviation ratio, because it's just kind of a one-to-one mapping. One's just the square of the other, so they both give the same p-values in this. And so again, if you did this permutation, it would look like it's not really any particular difference. Right? Now what's occurring to me is that this simulation, right, is we could end up with a case where if there's a mean difference in the groups and we're randomly sampling from that, that's not really only testing variances. Right? It's kind of testing any differences, right? And so that's not quite exactly what we would want to do just to test variances. So the better thing to do, right, so let's take the residuals. Take the deviations from the mean. In the two group. There's in one of these and there's in two of those. The variance of these, so s squared 1, is equivalent to the s squared. If you do the standard deviation, the sample variance on the y's, or the sample variance on the e's, they're the same values. Right? The first thing you do in calculating this is subtract the mean here, so it's just shifting everything over, so it's still the same spread value. Right? S2 squared equals SE squared. Right? So what I would suggest for the permutation simulation, instead of randomly mixing up the y's, because the y's could be small values and large values, right? So there'd be a mean shift as well as variability. If we only want to focus on variability, then we should get rid of the impact of differences in means. So permutation to test equal variances. Right? And then we can put the E1, I1, EI2, all of those values together. To get a random permutation, randomly pick N1, and that will give us an SE1 squared, that'll, an artificial one. Right? The other N2 of these residuals will go, we randomly represent the second group. Right? And so we can get a ratio here, a star ratio on the deviations, and S2 squared of those. Right? And so this should be free from the fact that the groups have different means. Right? If I just mix up the Y1, Y2, I could get a very large variance here or a very large variance here, just because I get some small values and big values from the different groups. But if we want to focus on the question of spread within the groups, we can take out the influence of the different means by permuting all these residuals. So can we do that in R and make that work out? So let's make this bigger so we can do a little code. All right, so what we really, instead of doing time, make a little modification here. Right, so we'll call something time deviation. We'll make it time, and then time deviation when the treatment is conventional is, well, let's make a little indicator. Treatment equals conventional. And so the time deviation for that group, right, is going to be the time minus the mean of time for that group. Right? And the time deviation when it is not that group, it's going to be time when it's not that group minus the mean of the time when it's not that group. So all that runs. And so instead of computing things here for time, I'm going to put the time deviations in here. And otherwise it should be the same. So we run that, and then the output. Does it change things very much? This is the histogram. So it changed the shape a little bit, right? It looks like we're even, maybe we're a little bit further out. So I think that the variance ratio before was kind of inflated a little bit because there was a mean difference. So maybe this is better. It still gives a p-value 0.074, so not quite as extreme as those other things. Well, yeah, a little bit closer to unequal, right? So that would seem to make a little bit more sense. So you can test variances in a few different ways, right? But any questions? I think we'll do these last two bits, like the simulation of procedures and should you do pairing. We'll kind of conclude on Monday. We're just where we started at 9:45. So we have 10 minutes, right? So so I can do one of these things, right? So it's not too long. It's more commands, right? So we talk about doing these different tests and maybe wanting to do different tests for different reasons, right? So how do we see that? So we're going to generate some data when the data are normal to begin with. Right? We're going to generate some normal data and some other normal data. R norm, mean 0, variance 1. So this null hypothesis is true. And then we're going to test, either using equal variances or unequal variances or this Wilcoxon test, right? And so we hope that we do not reject, right? We only want to reject about 5% of the time, right? Because it's a 5% significance test. We're going to generate 10,000 data sets, sample size 10 in each, and do these tests. And it takes just a minute, a few seconds there. So for the equal t-test, we rejected, was our p-value less than 0.05? Just about 5%. It's pretty close, right? A little bit more, but this is a simulation. Right? If we did 100,000 or 1,000,000, because all the assumptions are true. It really is, right? A true null hypothesis, normal assumptions all work. For the unequal one, it's also pretty similar. For the Wilcoxon, it's also less than 0.05, which is good. It's not quite as powerful, right? Instead of dealing with the actual data distribution and the averages, it's reduced information to ranks, right? So it's given up some information, and it rejects a little bit less often, which is fine. It's still, at least 5, no more than 5%, but it's a little bit, if you tabulate, there we go. It looks like so this is a table. On the left is, do you reject when it's equal, yes or no, true or false? And on the right, do you reject when it's unequal, true or false? Mostly for the same data sets, they're doing the same action. It's just the equal one rejects a little bit more often on a few data sets. The comparison to the Wilcoxon is a little bit more mixed. It's a little bit less consistent. But let's redo the simulation, but now the Y data has bigger variance, right? So now the Y data has standard deviation of 4, and the sample size is only 10, so this is kind of a small sample size versus 1, right? So now if we do equal variance, it has to estimate that kind of composite variance, right? 1 in 16, it's going to estimate it, to be kind of a big value, not very accurate in that sense. Right? So what happens to our testing as we do that? If we run this simulation, the equal variance one rejects a little bit more, right? About 0.575. Right? So it's a little bit more than 5%. And although this is simulation, that's getting up there a little bit higher. It's not, it's not 10% or 20%, but it's still, getting a little bit out there. The unequal one is still pretty close to 5%. Right? It doesn't go quite as much. And the Wilcoxon one, well, it seems to have kind of gone a little haywire, so I don't know. The Wilcoxon is really testing a different hypothesis in some sense, right? And that's really the explanation. So it's not only testing equal means, it's just taking its distribution is different, right? So it does want to reject more often because one's this narrow normal and one's this spread out normal. So Wilcoxon does want to reject. The t-tests are, the null hypothesis is still true. The means are both 0. So it's still, the t-test aim for 5%, but the Wilcox, because it's more general hypothesis, doesn't quite aim for that. You could rerun this with an outlier. Right? So this kind of funny code, I wanted to put an outlier up here near 3. Right? So make one of the last y value about 3 with a small chance of being around 3. I could have made it exactly 3, I guess. But if I make that 3, I want to make all of the rest of the y's a little bit lower on average so that the overall average is still 0. Right? So if I do t-tests, the x's have average 0, and the kind of y's over these couple lines end up with averages 0. Right? So we still want 5% for the t-tests. Let's see what happens when we do this one outlier. Right? We rerun that, and then do the tables. The equal one is rejecting only about 1% of the time. That one outlier up there causes a big increase in variance estimate, and it doesn't end up being significant. The unequal one, I guess, is also having this. So they're just all rejecting less than 5%. The Wilcoxon one apparently must be 2. Yeah, so you would generally think about rejecting about 5% of the time when the null hypothesis is true. And this is rejecting a lot more. That one big outlier is pulling up the mean and causing it to be rejected more. Even the mean is 0, but still. And you can simulate skewness with an outlier and see how it goes. Skewness with an outlier. All right, if we do those, how much do they reject? Even less. Wilcoxon is about 5%, so that's kind of interesting. So some of these procedures reject too often, some are rejecting a little bit more with these different simulations. And so the process, we're talking about how do these things perform. And we'd like to know that our 5% significance is at least 5% significance. We'd like it to be pretty close. Because if it's really hard to reject and can't do it, then when it's not true, it's not going to work so well. So that's the alpha levels or the significance levels are important. And this is the flip side of power, being able to reject is important. So we'll start looking at that. And I think then on Monday, we'll look at, if you had your choice of designing a study and doing paired or unpaired, what would you think about in terms of doing? And then we move on into chapter 5, looking at, analysis of variance, multiple groups. Good. Have a good weekend.
I have to work.
Debut yesterday. Oh, so, guys. Yeah.
Thank you.
Bye, Annie.